When discussing acid derivatives, I think the most important aspect is to understand how to interconvert one acid derivative to another. So, acid derivative interconversions. I have one acid derivative, I want to make a different one. If you notice, I can't talk and write at the same time. Okay, very difficult. So, acid derivative interconversions. Let's make that plural. So, the parent of the class is the carboxylic acid. So that's where we will start. And it's more than that's where I want to start. When you go through a chemical catalog, what you can almost always buy is a carboxylic acid. You may not be able to buy the different derivatives, but the parent acid is almost always available. So if you're going to be able to buy it, it's probably the acid. So that's a common starting point. The first and most common reagent we're going to encounter in acid derivatives is this reagent. It's called thionyl chloride. Thionyl chloride is a really reactive substance, SOCl2. And what it does with carboxylic acids is it converts the carboxylic acid to an acid chloride. Now, what we're going to discuss in this entire unit, and we're going to see over and over again, is that to interconvert acid derivatives, in the end, we need some kind of nucleophile at some point to attack our carbonyl. And the problem with carboxylic acids is that they are weak electrophiles. So in order to interconvert our acid into other desirable acid derivatives, we need to do something to make the carbonyl more electrophilic. And that's what the acid chloride does. So because of this chlorine, and it has this nice inductive effect, it enhances the electrophilicity. So this is, let's not say it's super strong, but it is a stronger electrophile. Turns out this reaction is very simple. You take the carboxylic acid, you dump in a whole bunch of thionyl chloride, you boil it for a little while, and then you remove the thionyl chloride, which is very easy to do. It's very volatile, and you get your acid chloride. So from here, once we have the acid chloride, we can treat this with a lot of different nucleophiles. And these nucleophiles are going to attack the carbonyl, push those electrons up, and I'm not going to show a full mechanism. Well, let's go ahead and show the full mechanism. We have a nucleophile, kicks these electrons up. What do we get? We get a tetrahedral intermediate. Now what we've seen up till now is we've always protonated the tetrahedral intermediate. We're going to change that. Now we have this chlorine. We have a leaving group on the carbonyl, on what was the carbonyl carbon. So we can bring those electrons down, kick out the chloride, and we get our nucleophile in place of our chlorine. And if we go way back, it's actually in place of our OH group. So we've done a substitution, not an SN2 substitution. This took 2 steps. We made an intermediate, specifically the tetrahedral intermediate. So how this is an acid derivative interconversion is our nucleophile is going to involve atoms like an O- or a nitrogen. So we're going to put other electronegative atoms like oxygen or a nitrogen in place of our original chlorine. And so we're going to make acid derivatives this way. And this could be something like an ester or an amide. Now very often, once we're done, we want to convert our new acid derivative into a different acid derivative. There are some shortcuts for that, but a really common solution is to just, let's take our acid derivative that we've made and cook it up with sulfuric acid and water. And what that does is it does a hydrolysis, and you hydrolyze your acid derivative to your parent carboxylic acid. And then once you have your acid, you convert it to the acid chloride here in the middle, and then you can put a new nucleophile to make a new acid derivative. So this is kind of the cycle of acid derivatives. We're going to go a circle. We can go from the acid to the acid chloride to a new derivative, and then back again to the acid by hydrolyzing with acid and water. So this is a cycle, and we will see this repeat itself over and over again as we look at different acid derivative problems.